Hello everyone. Today we will study about transform and conquer design strategy and how to construct a heap tree under transform and conquer design strategy. First we'll see what is transform and conquer design strategy. As the name itself tells, transform. Transform means it transforms the every instances of the problem into another form, and that form is the simpler or easier than the previous instances. Like that, in every iterations it transfer into new form, and that form is easier than the earlier form. This procedure is repeated until you'll get the final solution. So that is what you call as a transform and conquer design strategy. So now, as I told earlier, let's see how to construct a heap tree under transform and conquer design strategy. Before going to study about how to construct, first we'll see what actually this heap tree means. Heap tree, it is a binary tree, but in the binary tree, for every nodes you will have the keys. Okay, in the heap tree it is binary, but it contains the keys in a nodes, and along with that you have the two criterias, and these two criterias, if it fulfills, then only we can call that one as a heap tree. What is those criterias? Let's see. First one is, it is essentially complete. That is, all its levels are full except possibly the last level where only some rightmost keys may be missing. Meaning of this one is what? So it is a complete binary tree, but it is essentially means what it is, almost it is complete. Last one right node if it is missing, as you can consider that one also as a heap tree. Next one is, key at each node must be greater than or equal to keys at its children. So meaning of this one is, parent key must be greater than child node. So here these are the two criteria. First one is essentially complete, and second one is parent node key must be greater than child nodes. These two criteria, if it fulfills, then we can call that one as a heap tree. Let's see, for example, this is binary tree and this one is the essentially binary tree here, essentially complete binary tree. See here, okay, in all the levels nodes are full, but in the last level one node is missing. Which node it is? That must be rightmost node. If it is missing, then you can call that one as a essentially complete, as it is essentially complete. First criteria is fulfilled. Next one is what? Parent node. This is the parent node for this child node. So this one we call as a key. So what is key now? 7. Parent key is 7 and child key is 1. As 7 is greater than 1. Same thing you have to check for the remaining also. For this 5 parent key, 4 and 2 are child key. As 4 and 2 are, as it is lesser than the parent key here. Next for the 10, 5 and 7 here, child key, as 10 is greater than the 5 and 7. Is all the criteria fulfilled. All means here two criteria of the heap tree are fulfilled. That's why it is a heap tree. Next we'll see one more example. See, in this example it is not a essentially complete. Essentially complete means what? Only one node if it is missing, that to be rightmost node if it is missing, but along with this rightmost node even leftmost node is also missing in this tree. That's why it is not a essentially binary tree. If it is not a essentially binary tree, then it is not a heap tree. Okay, this is one more example. In this example, S, it is essentially complete binary tree because only right node is missing. Along with this criteria, you have to check one more criteria. What is the one more criteria? Parent key must be greater. So for the 7, 1 is, yes, it is child key, it is less. But for 5, if you see, 2 is less, but 6, okay, child key value is greater than the parent key other than parent key's value is greater than child key. So meaning of this one is what it is. This condition is not satisfied here because parent key value is not greater here. Second criteria, if it is not fulfilled, then also it is not a heap tree. So for the heap tree, both the criteria must be fulfilled completely. If both the criteria are fulfilled, then only we call that one as a heap tree. Okay, is it clear what is actually heap tree? Okay, next, heaps arrays representation. So now this is your heap tree. Now actually if you want to check whether it is a heap tree or not in the form of the program. Okay, if you want to implement a program and with the help of that program we want to check that whether it is a heap tree or not. We can't take this tree as it is as an input. Then you have to convert this tree in the form of the what? In the form of the input that your program can accept. That is the array representation. So now to represent the heap tree, we are using array, that to be one dimensional array, and 1, 2, 3, 4, 5, 6 are the index of the array, and 9, 5, 3, 1, 4, 2 are the keys of the heap tree here. So now for constructing the heap tree, you are using one concept, that is top down. Top down means what? From top to bottom you are considering the values, and from left to right order. See here, this is your top node, that is having the key as a 9. Next, left 5, right 3, left 1, right 4, left 2. See, this is the values how you are considering in the array here. And along with this, some more points are there in the array representation. First one is left child of node j is at 2j. For example, if this is your parent node and for this left node, so in the array usually you check the where actually this parent node is there. So now this is your parent node and index of the parent node is what? 2 here. So then usually you will get the child node in the 2j. This is your j now. 2 into 2, 4. See, in the fourth index you will get the left child here. As for the 5, 1 is the left child. In the fourth position you are having the left child key here. Next is right child of node j is 2j plus 1 here. For this one, right child is 4 here. Let's see. So now for this 5, index j is 2. 2 into 2, it is 4. 4 plus 1, it is 5. So in the fifth position, what is the value you are having? That is the 4. As 4 is what? It is the right child. Okay. So next is parental nodes are represented in the first n divided by 2 locations. N divided by 2 locations. For example, if this is the example, how many nodes are here? 6 nodes. 6 divided by 2 means what? 3. So first 3 nodes, usually it contains the parental nodes, and second remaining nodes contains the child node. We can divide it as a 2 half parts. First half part contains parental nodes and second half part contains child nodes. See here, 9 is parent node and 5 is parental node and 3 is also parent node here. That's why in the first half you are having the parental nodes 9, 5, 3 and 1, 4, 2 are child nodes. That one you are represented in the second half here. Okay. So this is how you represent the arrays using represent the heaps using arrays here. Next, how to construct a heap. Heap construction for the given list. This is your list 2, 9, 7, 6, 5, 8. Let's see how to construct a heap tree for this given list. So first you have to take the node, this first element as a root node. Next you have to start inserting the remaining elements left, right like this. Root 2 is a root node, 9 is left child and 7 is right child. Next 9, 6 is left child, 5 is right child. Next 8 is left child, next is right child. Like this, left, right you have to go and insert here. So now after inserting, you constructed a binary tree. But now you have to check whether it is a heap tree or not. Is it heap tree? So when you tell him it is a Heap tree, if it fulfills those two criteria. What are those criteria? Partially or essentially complete. As it is essentially complete, only one right node is missing. Second one is what? Parental key must be larger. So here child is 8 and 7. It is not larger. If condition is not fulfilled, then simply what is the thing you have to do? You have to swap these two keys. If I swap, I'll get 8 here and I'll get 7 here. Yes, now this one is changed after swapping, and based on the your Heap tree, this condition is satisfied. First you have to start with the last label and the last node. For this node, you are done the changes. Next, you have to check for the 6 and 5. 6 and 5 are child keys. For this one, 9 is the parent key, as 9 is greater than 6 and 5. As it is satisfied. Next, you have to go to the next level, that is your middle level. So, in the mid level also you have the two child keys, that is 9 and 8. But this 9 and 8 parent key is 2, as 2 is not a greater here. If it is not greater, then it violates second criteria. If it violates, then you have to make modification. How will make modification? By swapping. While swapping, you have to check among these two which one is the greater one. So among these two, which one is larger here? 9 is larger. Then you swap 9 and 2 here. After swapping, you will get 9 here and 2 here. Yes, in this level, that parent node 9 is greater than child keys 2 and 8. Now after that, once again you have to check to the last nodes also. See here, this is 2 is parent and 6, 5 is child keys. But it is criteria is not fulfilled because 2 is not a greater. If it is not greater, once again you have to interchange. While interchanging among these two, which one is larger? 6 is larger. So now you have to interchange 2 and 6. So after swapping 2 and 6, you will get the values here. So 6 comes here and 2 goes here. So now this is your Heap tree. So now in this way, you have to check whether it is Heap tree or not. If it is violates, okay, that the parent key and child key values condition, then simply you swap those values. After swapping, if you get the Heap tree, then you stop. Otherwise, you have to repeat until you get the solution here. So in this way, you can construct a Heap tree here. And see, transform and conquer. See here, in every iteration, you are changing the instances. 7 and 8, you are changed here. And here also, 2 and 9, you are interchanged. And 2 and 6. Like this, you are transforming the instances, and like this you will transfer on every iteration. When you will get the solution, then you will stop the procedure of the transforming. That's why you call this one as a transform and conquer. Is it clear now? Same thing, it is represented in the form of the algorithm, and you are representing that one using natural language here, and here you are using the word as a bottom up. Bottom up means what? I started interchanging from the which node? That is the last level and last node. That's why you can also call this one as a bottom up approach to construct a Heap tree. Is it clear now how to construct a Heap tree? Okay. Next, for example, already I have the Heap tree and now I want to insert a new key. If I insert the new key, then what changes is required if I want to get as a Heap tree? Let's see. Now earlier this is your Heap tree, and according to condition S, you already proved that it is a Heap tree. Now I want to insert a new element as 10. After inserting 10, is it Heap tree? No, it is not a Heap tree, because once again it violates the second criteria. What is that second criteria? That is parent key must be greater. But 8 is not a larger value here. Then what is the thing? If it is not, you have to swap these two values. So now after swapping, you will get the things. 10 comes here and 8 goes here. So now once again you have to check after swapping these two, okay, whether in the other levels also it fulfills the second criteria or not. In the low level, yes, in the last level that criteria is fulfilled. Next I have to check in this level also, in the middle level also. So for this middle level, this is your parent key, and parent key value is what now? It is 9. So it is not greater than 10 here. So if it is not, then it violates. Then if it is violates, you have to swap this two. Now if I swap, 10 goes here and 9 comes here. So now in this way, after inserting the any new element to already generated heap tree, then also after adding any nodes, if it violates, then you have to interchange until you will get the complete heap tree here. In the same way, if I delete the maximum element from the given heap tree, or how to delete the root node from the heap tree. Okay, delete the root node is nothing but the maximum, because root node contains only maximum element. See, this is the parent node, and this parent node always must be greater here. So that's why in the examination you may get the question is what? How to delete the maximum element from the given heap tree, or how to delete a root node from a given heap tree. For both the question, answer is same. Let's see, now I want to delete this maximum element 9 here. For deleting that, first step is you have to interchange last key with the root key here. So which one is your last key here? This is your left child key, that is having the value as a 1, and root node is value is having the 9 here. 9 and 1 you have to interchange. If I interchanged, then I'll get the result like this. Root node, that is 1, and last node, that is 9 here. And after that, now thing is what? You have to remove this node now. Now I want to remove this 9, and I remove that. After removing that, you have to check, so is it heap tree or not? Now it is not a heap tree, because thing is what it is? 1 is the parent node and 8 and 6 are the child keys. These values are greater than 1 here. Then what is the thing? It is not a heap tree. If it is not a heap tree, what is the thing you have to do now? You have to interchange. You have to construct a heap tree. How you have to construct? You have to swap the elements now. 8 and 6, which one is larger? 8 is larger. You interchange 8 and 1 here. So 1 comes here and 8 goes here. So whenever 1 comes here, this 1 is the parent for 2 and 5. As 2 and 5 is once again, it is greater than the 1 here. 1 is having the value lesser than the child key here. That is not the criteria. Once again it violates. That's why once again you have to interchange here. Among these two, which one is bigger now? That is 5 is the larger one. So now you have to interchange 5 and 1 here. So after interchanging, you will get 5 here and 1 comes here. So now you see, is it heap tree? Yes, it is heap tree. So in this way, you can also delete the maximum element or root node from the given heap tree here. After deleting the nodes, once again you have to check whether it violates your heap tree criteria or not. If it violates, then once again you have to swap and you have to construct a heap tree. So same procedure it is explained here. Root deletion and heap fix up here. Okay, you can read, you will get the concept here. Okay, I hope you got the concept what is heap tree and how to construct a heap tree, and how to insert a new element to a heap tree, and how to delete a root node or a maximum element from a given heap tree, and also what is transfer and conquer. Is it clear now? Okay, thank you.